Alrighty, folks, here we go. So you asked for number 2. Folks, remember, you do not have to work along with me, but you have to be quiet enough that I can hear myself. So that's very much appreciated. Thank you. Alright, so this one, they ask you about, you okay there, Mr. Jack? Okay. I wonder if we got that on video on the mic. So this one, they ask you all about work, right? So I think it would be a good idea to make sure you explain in your why that you understand about work. So that's why this is one of the few from this one that I would not actually use a energy diagram on. I think there's 1 or 2 or 3 at the beginning with work that don't need energy diagrams, and the rest of them do. So I would definitely show my understanding of work. You know, that work is done when a force is applied through a distance or something like that. You know, and I would even point out in this one, all distances here are vert, and so all forces are opposed. No, because you are demonstrating by doing it ahead of time that you're ready for class. You are less ready for class. All right. So that's what I would put for the wall. All right. So that's basically our equation. We would need also to remember that weight is that relationship, and that's kind of all there is to this one. So you are given the mass of it. I'm assuming it's on Earth because it's a can of paint, and you're told what height you lift it to. So I might even do a little sketch here next to what I was doing. I've got this can of paint. I've got to apply a force in this direction to balance out its weight in this direction, and I move it, in this case, 1.8 meters in that direction. So the work I do is going to be the force and the displacement in that direction. The force I'm going to use is mg, and I'm moving it whatever distance that tells me. So then it's just math after that, right? Yep. So we can skip that. And 1.8 meters. Good. And then on to part B, right? Part B, you hold the can stationary for half a minute waiting for a friend. How much work do you do during this time? Well, I'd apply the same idea. I would again do my sketch just to remind myself that it's still going to take force, right? But I don't move at any distance, so how much work is done? Hey! Moving on to part C. In part C, Not to use the paint, so you lower it back to the ground. How much work do you do on the can as you lower it? So, again, personally, I'm going to start with a sketch. I'm going to have to still put a force on this because I'm going to assume that I'm lowering it without just dropping it. And so I'm going to consider that I'm using the same amount of force. But what is true of my displacement and my force in this case? Which one? Yeah. So the distance is negative, but my force is still positive, meaning negative work is done. So if I look at it as the sense of the can, I'm doing negative work. I'm taking energy away from it. Because when I lifted it up, what type of energy did the work I did on it give it? Huh? I heard someone with the right answer. Potential. What type of potential? Gravitational potential. And then when I lower it, what's happening to that gravitational potential?
Lowering.
It's decreasing. It's going away. And that's why it's negative work. Remember, external work always adds or takes away energy. So I would do C exactly what I did A, except I'm going to get a negative answer. All right, number 4. You got a bicyclist that rides his bike with the speed of this. Ooh, right away, you're thinking what type of energy, since they tell you speed? Kinetic energy. And they ask, how much work must be done by the brakes to bring the bike and rider to stop? Oh, so things are changing, so right away I must think about doing an energy bar graph. And then they ask me about what is the magnitude of the braking force if the bike and rider comes to rest in this distance. And I see force and distance, and right away I think about work. So not only do I would say if I was doing this one on a test, I would do an energy bar graph, but also then a little diatribe about work to show I understood what work was. But let's see. So to start off with, are we going to have any other type? We have kinetic energy. Are we going to have any other type of energy when the bicycle is moving along at that speed? No? Okay. So we'll leave the other columns blank. All right? What about after? After they apply the brakes? Nope, just stop. It hasn't changed height or anything? All right. So I think we're pretty safe with just using the columns as they're labeled. So I'm going to start off and say, okay, well, my cyclist has that much kinetic energy. And then work is applied externally. The brakes are an external work because they're taking the mechanical energy and changing it into non-mechanical energy through the use of friction. And at the end, I'm not moving, so I don't have any more kinetic energy. So I must do as much work as I had kinetic energy, right? Because remember, the initial system energy plus the work external must equal the final system energy. So that should have been your bar graph. And of course that leads us directly to our equation, which says KE initial plus negative work, let's say by the brakes, must equal 0. Oh, that's nice that it led us directly to the relationship we needed. Could that be why Mr. Cochran asked us to do energy bar graphs on these? Perhaps. But he's not that nice. He's meaner than that. Must be some type of trick. Kind of like those force diagrams that directly gave us the force relationship. Oh, perhaps. Oops. And that just equals the work by the brakes which is, I believe, what they ask us for part A, right? Now notice, what units are they suggesting we use?
Kilojoules.
Kilojoules. If you don't want to use kilojoules, just rewrite it as joules. But if you leave it as kilojoules and just ignore that, your answer is going to be wrong.
Wait, are kilojoules?
I'm not going over prefixes.
No.
Do you have study things? Unless we want to start having quizzes on prefixes. No? Okay. Then I'm not going over them. That's something you learned in middle school. Mass of the rider, mass of the bike, speed initial squared equals, and you can just fill in, right?
Yes, sir.
Good. And then in part B, we're going to use our work. And you have the work from part A. You're asked to find the force, and you're told the distance. For me, I think it was 35 meters. 3.5 meters. And yay, I'm all done.
Is it like
You guys know how to do arithmetic and algebra.
Is it like where it says come to rest at? No, A.
All right, number 5. We've got an apple falls from a tree to the ground. We're ignoring air resistance. So right away, if they tell you ignore air resistance, do you think there's any external work? No. Determine the apple's kinetic energy, gravitational potential energy of the system, and the total mechanical energy of the system when the apple's height above the ground is 3.0 meters. So not quite to the ground. All right. Shocking. Energy bar graph. So when the apple is 4 meters in the air and just attached to the tree, what type of energies are we going to have there? We're going to have kinetic energy? No? Excellent. PE graph we're going to have? You are. Any other types of energy? Before or after? No? Pretty good? All right. Let's see. So when it's hanging from the tree and not moving, I'm going to say no kinetic energy. Okay. But a lot of potential energy, gravitation. Lots of it. They said to ignore air resistance, so that tells me no external work. And then when it's, is it at 3 meters or 3 meters below? Nope, apple's height above the ground is 3 meters. So really, how far has it fallen? 1 meter. Maybe a diagram would be helpful for those of you struggling with placement. Tree. This is at 4 meters. Happy little apple. And then it falls, and they're saying at 3 meters above the ground. Right? I mean, I find pictures much more helpful than words. But, you want a physics coloring book? I have one. So, what's changed? I mean, we haven't lost any energy, right? Because we have no external work. But what's changed? It's kinetic. So it's changed some of its potential gravitation to kinetic. So let's give this a little bit less. And we'll make up the difference right here. Right? Is that good? And so this was when it was at 4 meters. This is when it's at 3 meters. And I know it'll shock you, but we get an equation from that, right? We get PE grav at 4 meters equals KE at 3 plus PE grav at 3. Notice, am I writing those equations in my hows or my whys? In my hows. Because you never put equations in your why. Alright, so let's see, P grav. Oh, that's mgh. KE, that'd be h4. KE is 1/2 mv squared. And this is mgh3. Yeah. I know it's potential energy gravitation, so I put the P and the E for potential energy. Although you could use the symbol U, and then the subscript G indicates gravitation rather than like electric or spring or something. And the 4 I did because that's when we're at 4 meters of height. So I had to label it some way to tell the difference between them, and I chose what height. I understand my T's look a little like 6s. Monday morning, cut me a break. That's okay. No. There's no offense to my look. I hope. All right. You can probably take it from there, right? No? No? Well, let's see. They want the energy total. Right, let's see what are the things they ask us for. They ask us for kinetic energy. Right? But it's at 3. Oh, that's that. Right? That's KE at 3. Oh, I've never written right above it. So you can solve for that, right? Because you have M? Yeah. How do we know what little g is? How do we know it's 9.81 newtons per kilogram? No, it isn't always, Joe. How do we know we're on Earth? There's trees. Any other planets we know of have trees? Nope. Now use your contextual clues here to help you. Do we know the height at 4 meters? Anybody? Do we know how high the apple is when it's at 4 meters high?
Yeah.
Okay, good. So we know everything in here. Oh, we know the mass. We know G. Do we know the height of the apple when it's at 3 meters high? 2 meters, right. Good. Oh, so we know, let's see, we know everything in here and everything in here. Do you think you can find the value of this thing together? Probably. I have faith in you guys that you could find that.
Are you supposed to find everything individually?
Well, I'm going through what they're asking for, right?
Yeah.
Okay.
Okay.
They are. PE grav. So let's see. Do you guys think you can find this value here? Easily. Alright? And then the third one they want is the total energy. How could we find the total energy? We could find the left value here. So this would be the energy total. Or we can find the right value, right? Because they're equal. But I agree, it'd be easier to find the left one. So, let's see, that is that one. Oh, so all three of them make that up, and I think guys can do it from this point. Why don't I give you a couple minutes and you tell me if you have problems, I'll come over and talk to you, okay?